Mhm. Hassan beta, kindly mark your attendance in a chat box, okay? And also ask your class fellow to join the class. It's 9:35 and still there's no one. Okay, are you seeing the screen? Unit 15, electromagnetism, conceptual questions.
Yes, ma'am.
Okay, okay. First of all, open your book, page number. Open page number 150 because I don't have diagram in these slides. So it's better when the question that are belonging regarding the diagrams, you have to look at the book, okay? Okay. The question number one is two parallel straight conductors carrying current in same directions, right? We have two conductors, and these two conductors, they are having the same direction of current. So that's and they're asking, they attract each other. Explain why. What will you conclude if direction of current in conductor is opposite? So the two parallel straight conductors will attract each other if current in the same direction in both, and will repel each other if the direction if the current in the is in the opposite direction. Now we will see the explanation that how it will work. When the current in the same direction, the magnetic field is in the opposite direction, right? See, if this is the one conductor, this is the other conductor, and it has a magnetic field. Wait, not touched. Okay, actually, I can't draw on this. Wait. So, right, if we have two conductors that are parallel to each other, so the magnetic field that are start to develop around this conductor is in opposite direction. So when the magnetic field is in opposite direction, it's mean that these two conductor, they will be attract each other. But if we see the case in which the direction of the conductor is in opposite direction, so what will happen? See, if these are the conductors, right? And I will draw a magnetic field around this, right? So what will happen when the current, they are in opposite direction? Let's suppose the current in this field is in this direction, and in this conductor the current is in this direction, right? So they will have the same poles, right? So direction will be same like this. So it's mean they will repel each other because the direction of their magnetic field is same. So when the direction of the magnetic field is same, their pole will be same. Obviously, if this will be a north pole, this will also be a north pole, right? So we know that north pole will repel with north pole, right? And if this is a south pole and this is also a south pole, right? So these two south poles, they are similar to each other, so it's mean they will also repel each other. So when the current is in opposite direction, magnetic field is in the same direction and behave like a similar poles to like a magnetic pole. That's why this is the reason that they will repel each other. Okay, so the next question is, bar magnets are dropped in long pipes made up of plastic and copper of same length. Simultaneously, bar magnets come out later through copper wire than through a plastic pipe. Why? So first of all, we have to know the nature of the plastic and copper. So Hassan, can you tell me what is the nature of plastic and what is the nature of copper wire?
Ma'am, plastic is an insulator and copper is a conductor.
Very good. That is the reason plastic plastic is a non-conductor in which we place in a category of an insulator, and on other side the copper wire, copper wire that we use in the shape of a pipe is and behave like a conductor, right? So bar magnets come out later through copper pipe, because when bar magnet are passing through a copper being a conductor pipe, and induced current is produced in the pipe. How the induced current is produced in the pipe? We know the nature of the conductor, that one conductor is connected with any it is placed in any placed in a, we are providing a potential difference or voltage to a conductor. What will happen? The field is induced around the conductor, right? So when field is induced around the conductor, so what will happen? It is also a reason there will be a number of magnetic line will be developed, and these magnetic lines are capable, or we can say that they are a reason to induce a current that is produced in a pipe. So this induced current oppose the cause of motion of a bar magnet, because the bar magnet, it also contains the magnetic lines, right? And the induced current, obviously it is producing due to the magnetic field lines, right? So both they will induce oppose each other. No such effect of plastic as an insulator, because if we connect the plastic to a potential difference, or we are providing the current to the plastic, what will happen? No current will be flow in the plastic pipe, right? That's why the bar magnet came out later through copper pipe than the plastic pipe, right? So here I also draw a chart for you, simple, that you can it that if we induce the current when the magnetic field is produced around any conductor, this magnetic field is the reason to generate a magnetic flux. And obviously in the start we are providing the voltage that is an alternating voltage. So obviously the magnetic flux will be changed. Due to magnetic flux, EMF will be induced, and due to this EMF, uh, current will be induced, and this current will oppose the motion of a bar magnet. Okay, the next question is, okay, the third one is, what is the direction of magnetic force What is the direction of magnetic force on this current carrying conductor placed in magnetic field? Also label the diagram with current, magnetic field, and force. Okay, boys, take out your books. Open page number 50. There is a diagram on a book in which you are seeing that there are two magnets. If you open page number Open page number 150. There is a diagram in third question, right? I'm trying to draw the diagram over here. If these are the two magnets, right? No, we know that one pole is north pole and other pole is south pole, right? And in between we have placed a conductor, and this conductor is in this, the current is flowing in this conductor in this direction, right? So they are asking what is the direction of magnetic force on this current carrying conductor placed in a magnetic field. Also label the diagram with the current, magnetic field, and force. The direction of current in the wire from A to B is denoted by I. So what is the direction? This is point A and this is point B. So this current is basically flowing from A to B, like it is in the upward direction. That is mentioned in the diagram in the book that is given to us. And how and also we can find out the direction of the current by using the right hand rule, right? All of you know that what is the right hand rule. Right hand rule is when you grasp any conductor in your right hand, the thumb indicates the direction of a current, and we know that the direction of thumb is always upward. So here you see the direction of current is upward, right? The direction of magnetic field is from north to south, right? This is the north pole, this is the south pole. So the magnetic field that are generating and that we call the external magnetic field is in this direction, right? So we can say that the direction of magnetic field is indicated by our fingers. We know that the magnetic fields are represented or denoted by a letter B, and again we will apply we can say the right hand rule. Grasp a conductor in your right hand, the curling finger will indicate the direction of a magnetic field. So if you curl the fingers, again you will get this direction of magnetic field, right? The direction of magnetic force is up. Now here the direction of current is upward. The direction of magnetic field is from north to south. So what about the direction of magnetic force? The direction of magnetic force is vertically downward, denoted by F and indicated by a palm of a right hand rule, right? So we can say that the direction of force is always opposite to the direction of the current. So if the direction is in upward, current is flowing in the upward direction, magnetic field is from we can say that they are towards the right. From left to right, the direction of force will be downward. So you have to draw the direction of force like this. This is the direction of current, upward. This is the direction of magnetic field, and downward is the direction of force, and this force is known as a magnetic force. Now read the next question. Okay. Now again, keep your books with you for question number 4 as well. What is the direction of rotation of a coil shown in figure, right? So all of you know that the closed loop is known as a coil. So this is, if this is the coil, and this coil is connected with a commutator or carbon brushes like this. These are the carbon brushes. All of you know that we have already learned in the class. This is the south pole. This is the north pole, right? And these brushes, these are connected to the battery, right? And they are connected to the switch, right? This is the diagram. So they are asking, if we read the statement of a question, what is the direction of rotation of a coil shown in figure? So this is the coil. We have to find out the direction of rotation of this coil when the switch is closed. Label the diagram with the direction of force forming couple and rotation of coil. Okay, now who can tell me what is couple? We have already discussed in the class. We have learned this term in grade 9 as well. Can you define what is couple? Yes, Arif, can you define what is couple? Hassan, can you define what is couple?
Ma'am, when two forces move in the opposite direction, one in the
Okay.
clockwise and other in anti-clockwise motion.
Okay, we can define couple as when two forces they are having the opposite directions, mean the line of action of their force is opposite to each other, and we are using the two forces that we can say that they are the unlike parallel forces. So if the one force is in upward direction and other force is in downward direction, these two are known as unlike parallel forces. Why we are calling these unlike parallel forces? Because we know that they have the opposite direction, right? So if they have the opposite direction, their line of action of force is also different. So this force is in upward direction and this force is in downward direction, right? So these forces F1 and F2 are equal in magnitude, but they're opposite in direction. That's why they are forming a couple in this coil. A couple always lead to rotation. Here the rotation is clockwise. So it depends upon the from as we are this is the direction, this is a clockwise direction, right? So if we are applying the current in this direction, the direction of the of this coil will be anti-clockwise. Like if we say this is point A, this is point B, this is point C, this is point D, so CD will turn first and then AB will become on the other side. Then after this the direction of the coil will be like this. So they are moving in the clockwise direction. Now see a question number 5. Okay. Question number 5 is this is question number 5. Question number 5 is a bar magnet is moving in the ring. Okay? Right? So this is if the ring and we are going to move this bar magnet in this ring. What is the direction of induced current in the ring? We have to find out the direction of induced current. Induced current is basically from the current that is produced due to the magnetic lines, right? When magnet is moving towards the ring, the magnet is moving away from the ring. So we have to do case in which we have to tell what when magnet is moving towards the ring. So if there is a magnet and it is moving towards the ring, then what is the direction of induced current? And if we are moving the magnet away from the ring, then what is the direction of induced current? The direction of induced current in the ring will be anti-clockwise when magnet is moving towards the ring, right? So whenever we are moving the ring, magnet the ring, the direction of the current will be like this. It is in downward direction. This downward direction is known as anti-clockwise direction. Now we will see how this induced current is in anti-clockwise direction. When a magnetic flux is changing, right, an induced current will be produced in the conductor which will oppose it cause. When bar moving towards a ring, magnetic flux is increasing and due to electromagnetic induction, induced current is generated in the ring. This current will be in such a direction as to oppose the entry of a bar magnet, right? Because you know that why we are saying that induced current has an anti-clockwise direction, because this bar magnet is producing the magnetic lines. Also this ring is also producing a magnetic lines, right? So when both are producing a magnetic lines, so it's mean they will repel each other, so the direction will be anti-clockwise, right? The direction of the induced current in the ring will be clockwise when the magnet is moving away from the magnet. In this case, what will happen, the current is easily flowing in the ring and we are taking the bar magnet away from this coil, because this coil is also producing a magnetic field and other bar magnet is also producing magnetic field. When we bring close together to each other, the direction will be of current will be anti-clockwise, and when we take away the bar magnet away from it, the direction will be clockwise, right? Because we know that if we bring two magnetic field together, obviously they will be repel each other, and when they will repel each other, the direction of the current will be anti-clockwise. Now the next question is Why output of transformer is zero if DC voltage is applied on its primary coil? All of you know that when we are using the transformer, what will happen? Hassan and Reep, kindly turn on your cameras. Okay, it's not allowed to turn off the cameras, so you have to turn on your cameras. Okay, we know that the transformer its work on the AC voltage. We always increase or decrease the AC voltage. So it's not work on the DC voltage. So here is the answer that why the output of transformer is zero, because we are giving the DC voltage. When we are giving the DC voltage, the transformer is not increasing or decreasing the voltage. Obviously, it will give a direct voltage. So when it's give a direct voltage, obviously the output will be zero. DC voltage supplies DC current which remain constant, and magnetic field produced by constant current is also constant. A constant magnetic field cannot induce the current in the secondary coil, so output of the transformer will be zero. According to the Faraday's law, induced EMF produces only when there is a change in magnetic field. And also you can mention over here that transformer work on AC voltage. We never use DC voltage in transformer because the purpose of transformer is to increase or decrease the voltage. But if we are giving the constant voltage, how it will give us output? Any output? Obviously, when voltage is constant, the output will be zero, right? 7 is why are coils of transformers wound an iron core? So you have drawn the transformer in the class, right? Why we wound iron core over here like this? So the answer is the transformer works on the principle of electromagnetic induction, in which a current in primary coil induce EMF in secondary coil. This is the main function, main working of a transformer. Ideally, the rate of change of magnetic flux to the primary coil must be equal to the rate of change of magnetic flux in the secondary coil. To transfer a maximum rate of change of magnetic flux produced in the primary coil due to the change current in primary coil to the secondary coil, a good paramagnetic material must be used. That's why iron core is used in transformer. And we know that iron core is a conductor. Obviously, it will generate a very good amount of a magnetic field, and these magnetic field they will later work as to induce a current, right? So this is the answer of this question. Okay. Then question number 8 is what step up transformer is used for long distance transmission? So it's very important question that why there's a need of step up transformer. First of all, tell me what is the purpose of step up transformer? Yes, Ari. What is step up transformer? Why we use a step up transformer? Yes, Ari.
For long distance transmission.
In a step up transformer, we give high amount of voltage in output. That's why its name is step up, right? Because in secondary coil of a transformer, we get high amount of voltage. That's why we call it step up transformer. A step up transformer is used for long distance transmission because it increase the voltage but decrease the current. Obviously, when we increase the voltage, the current will be decreased by using Ohm's law, and it will decrease the power losses, right? Okay. Now the next question is number 9. When you are pushing a bar magnet toward coil of single turn, you feel an opposing force on your hand, right? If this magnet is pushed towards the coil of the many turns, now you will feel greater opposing force. Why? When a bar magnet is brought close to a coil, obviously we know that the bar magnet is also generating a magnetic field lines, right? And the coil is also producing a magnetic field because of the current, right? So EMF induced in the coil, and it will oppose its motion, because when it has this bar magnet has a magnetic line, this coil has a magnetic line, they will repel each other. So when they will do both magnetic fields, they will repel each other, it will produce motion that will keep you away from these two, bar magnet and coil. That's why when we increase the number of turns of the coil, obviously there will be the induced EMF will also increase, number of magnetic field lines also increases, and the effect of opposing will also be much more greater, and we feel large repulsion, right? Okay, the last question is number 10. Question number 10 is, in what way split rings commutators in DC motors differ from, sorry, this is slip rings. This is slip ring. This is not split. This is slip ring. Okay. Slip rings in AC motor working, right? So obviously they are seeing what is the difference. So it means we have to make a column to write a difference. First of all, we know what is slip ring and other is split ring. This is split ring. Split ring. Okay, slip ring is used for transferring the power between the rotating and stationary structure of a machine, and this is used to reverse the direction of a current. Whenever we want to change the direction of a current, we will use a split rings, right? Now slip rings they are using in AC machine, and split rings they are using in a DC machine. AC machine we have a continuous ring, right? And a split ring we have two or more parts. Like if we draw the split ring, slip ring is like this, right? We have to connect it the carbon brushes. It's like a continuous circle. But if we talk about a slit ring is like this. It's divided into two parts. We can divide it into in even more than two parts, but in your book it is only divided into two parts. So this is known as slit ring, split ring. This is known as slip ring, right? So these are the question answers of your book. Now we will discuss one topic of unit 16, right? So just wait, I have to change the just wait, I have to change the slides. Okay, we have discussed one topic of cathode rays in school. So we are going to start the other topic, that is the thermonic emission. Now, what is thermonic emission? Therm mean heat, right? Emission mean out. Okay. So we are taking the heat out from thermonic means we are using basically electrons over here, right? So we are taking heat out from the electrons, or we are taking energy out from the electrons. So this process is known as a thermonic emission. Metals have free electrons, therefore they conduct electricity. So how metals get a free electrons? Free electrons are not bound to a particular atom and free to move randomly inside a metal. These electrons are most of the electrons that are known as valence electrons. We know that the outermost electrons are known as valence electrons. That's why they are known as a free electron. These free electrons are still bound to the material by characteristics. Binding energy is called metallic bonding, and energy required to break this bond is called work function. Work function is the minimum energy that must be given to an electron in order to eject it from the metal. Now we learn how this energy work function will be worked. You know the structure of an atom, right? So this is a nucleus. In which nucleus we have a positive charge, which is we carry this positive charge on the proton. So these are the shells of electrons, and if we see the outermost shell, there is the electron, right? So this is a valence shell, and this electron is only we have one electron over here, but this electron cannot leave this structure of atom or shell of atom. Why? Because this electron has the attraction force of attraction with this positive proton, right? So what will happen when we provide extra heat or extra energy to this atom? This electron will leave out from this valence electron and become as a free electron. So basically we work as a work function over here, right? We break it metallic bounding with the nucleus of that electron. So when we break this bound, this process is known as a work function. So work function is the minimum energy that is given to an electron in order to eject it from the metal. So in this way, when we provide the minimum energy to the electrons, they will eject it from the metal, and then they behave as a free electrons within the metal, and we call them as a free electron. Now if you see the diagram, in diagram where we have a hot filament, right? Hot filament, this hot filament is a substance and that is connected to the an EMF source, right? This is the EMF source. here we are getting the voltage from this, right? So what will happen when we are providing the voltage to this hot filament, the electrons, they are leaving this hot filament and they are coming out, mean we are ejecting the electron from this hot filament, and this process is known as a thermonic emission, right? So with the help of a battery, when we have created any conductor, mostly we use the hot filament. So hot filament, in which we have some amount of free electrons. So these free electrons, when they are when this hot filament is getting energy from the voltage in the form of a current and is getting hot, so the electrons, they are leaving their valence electron and they are become as a free. So this is the ejections of a metal, this case, right? So if we see the next slide, there is the definition of you have to write this definition in your notebook, right? Temperature induced electron injection is called thermonic emission. If sufficient energy is given to the metal, the electrons taking this energy will be able to overcome the work function, causing electrons to emit from the metals, means they are leaving the metals, right? Harmonic emission can also be achieved by passing electric current through tungsten filament. We have discussed in the previous diagram that we are using the tungsten filament, and when we are getting tungsten filament to the supplying the voltage, and this voltage is producing a current, so this current will heat up this filament and it will be helpful in to use the electrons that they are leaving the tungsten filament. The electric current heats the filament and the free electron inside the filament start to move faster and faster. Some of these free electrons may get enough energy to overcome the work function and escape from the metal. The higher the temperature, the higher will be the number of escaping of electrons. So it depends upon the how much voltage we are providing to this tungsten filament, right? You only have to write this definition in your notebook for your knowledge that you have done this topic. Now, the next is okay. So the next topic is electron gun and cathode rays. We have already learned uh, what are cathode rays, right? In the school that they are the negative particles. And now we are learning what is electron gun. The source that provide electrons. This source is given by the electron guns because we can take out a very large amount of electrons from this gun. Electron gun, it consists of a glass tube, and this tube has a very low pressure and it has a negatively charged. Obviously, we know that electrons is a negative charge, so we have to place a negatively charged electrode. And these negatively charged electrodes are known as cathode, and the positively charged electrodes, they are known as anode, right? The electrons are emitted through the indirectly heated cathode. We heat the cathode, and these electrons, they are emitted from the cathode. Indirectly heated cathode means the cathode's electrodes surrounded the filament and emit electrons when the filament is heated up the power supply. So again, we will use a tungsten filament over here, and when we use a tungsten filament connected to a battery, we know that this is the indirect method to take out the electrons. For getting the higher emission of electrons at a moderate temperature, a normal temperature, the layer of barium and strontium oxide is applied at the end of the cathode. The current and the voltage that we required for this process is 600 milliampere current is needed. And this 600 milliampere current is we get when we supply the power of 6.3 volt. Electron beam produced by an electron gun is also called a cathode rays, as these rays are emitted from a negative electrode as termed as cathode. The cathode ray passes through the control grid made up of nickel and have negative biasing which control the flow of electrons that I show you in the next slide, okay? So this is a diagram in which you are seeing there, right? So we are giving the voltage of 6 volt, 6.3 volt or 6 voltage, right? This is the cylinders. We are using the 3 different cylinders over here. it contains a filament. This filament is taking out, when we heat up, we get a, and this filament is working as a hot cathode. We are taking out the electron from it. This is a control kit. It will control the emission of electrons. The one by one electrons, they are coming out in this way. And the in here and these this tungsten filament and this accelerating diode, they're connecting with a very high accelerating voltage, that is about 100 to 5000 voltage, right? So this is the process by which we use the electron gun, and we are getting the cathode rays by using this electron gun. So this is the today lecture. If you have any confusion, you can ask me now, otherwise I have to end the class. Okay. Yes, Hassan, do you have any problem?
No, ma'am.
Okay, then I'm going to end the class. Okay. Okay.